We'll begin our course with a discussion of the basics of lasers and laser light, and what better place to start than the acronym Light Amplification by Stimulated Emission of Radiation. This is the definition of a laser. You may have an intense light source, but if the light isn't produced by stimulated emission, then you don't have a laser. This idea of stimulated emission came from work that Einstein did in 1917. It took us about 40 years to move from the theory of stimulated emission to the actual production of a laser. That was done by Theodore Mamam at Hughes Aircraft. The first laser that was built was a ruby laser. What we'd like to do now is take a look at a short video that discusses the basics of laser light and the properties, and then move into the components of lasers.
Basics of lasers and laser light. LASER is an acronym for Light Amplification by Stimulated Emission of Radiation. The stimulated emission process is the process that creates laser light. The radiation in lasers is just light, but it's a unique kind of light that creates unique hazards. Light is an electromagnetic wave. The wavelength is the distance between two peaks on that wave. Different wavelengths are seen by the eye as different colors. The entire electromagnetic spectrum extends from gamma rays on the short wavelength end to radio waves on the long wavelength end. Visible light is a little slice in the middle. Shorter wavelengths than visible are ultraviolet, longer wavelengths than visible are infrared. Lasers operate in the ultraviolet, visible, and infrared portions of the spectrum. When energy is added to an atom, some of the electrons in that atom move into larger orbits. Now, this is not a stable situation, and those electrons are going to drop back into smaller orbits and emit photons of light. Ordinarily, this process happens spontaneously, resulting in light of many different wavelengths that travels in all directions. In the laser, the excited atom is struck by a photon that stimulates the emission process. When a stimulated photon is emitted by an atom, it is identical to the incident photon. That means that the two photons have exactly the same wavelength, they travel in exactly the same direction, and their waves are locked in step, so they wave together. This leads to the unique characteristics of laser light. Laser light is monochromatic. That means it's all one wavelength. It's very directional. It doesn't spread out very much. And it's coherent. That means all the waves are in phase. Ordinary light lacks these characteristics. This combination of characteristics means that laser light focuses 100 times better than ordinary light. All lasers are constructed on the same basic design. The active medium is a collection of atoms that can produce light by stimulated emission. The excitation mechanism is an energy source that excites those atoms so they can emit light. The optical resonator is a pair of mirrors on each end of the active medium. The laser light bounces back and forth between the mirrors, passing through the active medium, getting stronger and stronger, and then some of the light passes through the partially transparent output coupler to form the output beam of the laser. Gas lasers use a gas as the active medium and electrical or radio frequency excitation mechanisms. Carbon dioxide lasers can produce thousands of watts, and they're widely used for metal cutting and welding. In solid-state lasers, the active medium is a crystalline rod. The most common of these is the neodymium YAG. YAG is a transparent crystal, and neodymium is the kind of laser atom that's embedded in that crystal. The excitation mechanism can be an arc lamp, or a flash lamp, or a diode laser. Neodymium YAG lasers vary in size from laser pointers to laser welders. Each laser produces a specific output wavelength. Visible lasers can easily cause an eye injury, but since the beam is visible, it can be controlled and avoided more easily than an invisible beam. Near-infrared light is focused onto the retina of the eye, but it cannot be seen because the retinal receptors don't respond to those wavelengths. This creates an invisible retinal hazard that is most likely to result in an eye injury. The greatest safety precautions are required for near-infrared lasers. Lasers operating in the ultraviolet or the far infrared can damage other parts of the eye, but their light does not reach the retina.
In summary, lasers have three main components. The active medium, this is a collection of atoms or molecules that does the lasing, produces the output, the laser output. The excitation mechanism, this is an energy source, could be a power supply, could be flash lamps that provide the energy to the active medium. And then we have feedback through the optical cavity. This is where the amplification happens, and it happens between the high reflector or HR mirror and the output coupler, where the output exits the laser or the OC mirror. Laser light has unique characteristics. It's monochromatic, meaning one wavelength. Now, we'll find out that lasers actually can produce multiple wavelengths at the same time, but compared to ordinary light, this output is a very narrow spectrum. Laser light is highly directional. We really like this characteristic of the laser because it allows us to deliver energy to where we want to do our work very efficiently. And then last, laser light is coherent. In other words, all the waves are in phase, which means they're acting in concert, they're acting together, and this gives us the intensity of the laser. The combination of these characteristics causes laser light to focus to a tiny spot, and because it can focus to a tiny spot about 100 times better than ordinary light, this is why it's so hazardous to the eye.